Hello everyone. So we go to the second lecture of this course on nuclear and radiochemistry. So far we have discussed the radioactive decay. We learned that radioactive decay follows the first order rate law, and we also discussed the different types of conditions, like the two independently decaying radioisotopes, how does the activity change with time, and also branching, a radioisotope decaying by two modes like beta plus and beta minus. So how does the half-life depend upon the partial half-lives? Today we will discuss the decay of an isotope to another isotope which is also radioactive. So there is a chain. The decay happens in a chain of radioisotopes, and so there will be different aspects of that and a lot of applications also which I will be discussing in this lecture. So when we mean by radioactive decay chain, I mean that a radioisotope to isotope A undergoes some decay to B, and B is also radioactive to which also decaying further to C. So we have already discussed the radioactive decay of A, which follows the exponential decay. So N1 is the number of atoms of A at any time, and which we discussed in the previous lecture that it follows an exponential decay with N1 0, the initial atoms of A, and the decay follows an exponential path. Now let us discuss how the activity of B will change with time if it is growing from a freshly purified isotope A. So the lambda values for A is lambda 1 and for B is lambda 2, and the number of atoms of A and B at any time t are N1 and N2 respectively. Let us assume the initial conditions that when time is 0, then there is no daughter product. We have only the N1 0, the initial number of atoms of A, and N2 is 0. So we set up a differential equation for the number of atoms of B, how it is changing with time, and solve that equation to find out at any point of time t, how does the number of atoms and hence the activity of B change with time. So let us see here the rate of change of number of atoms of B will be given by dN2 by dt. B is growing from A, so that is N1 lambda 1, that is the rate of decay of A is the rate of growth of B, and the B is decaying by the rate dNB by dt equal to N2 lambda 2. So there is a growth part and there is a decay part. Now this is a differential equation and we have to solve it for N2. So N2 is the number of atoms of B at any time t. So let us see how do we solve. First we separate the variables. So we say dN2 by dt plus N2 lambda 2 equal to N1 lambda 1, and N1 lambda 1, N1 we know, so we can write N1 0 e raised to minus lambda 1 t lambda 1. I have replaced N1 by N1 0 e raised to minus lambda 1 t. So such a differential equation I want to solve, then we can have, there is something called as the integration factor. This is e raised to lambda 2 t. If I multiply both sides of this equation by this factor, it becomes easy to integrate. So I say dN2 by dt e raised to lambda 2 t plus N2 lambda 2 e raised to lambda 2 t equal to N1 0 lambda 1 e raised to, it will become lambda 2 minus lambda 1 t. Now let us integrate this equation. So you see here, this term becomes the differential of n2 e raised to lambda 2t, and the differential of n2 e raised to lambda 2t equal to n1 0 lambda 1 e raised to lambda 2 minus lambda 1 t. So if I integrate, then you can see the solution of the integration of this will become n2 e raised to lambda 2t equal to n1 0 lambda 1 upon lambda 2 minus lambda 1 e raised to lambda 2 minus lambda 1 t plus c. So now you can now find out the value of the integration constant c, that is when t equal to 0 and 2 equal to 0. So if you put n2 equal to 0 here, this term becomes 0, and so it becomes c equal to minus of this term. So c becomes minus n1 0 lambda 1 upon lambda 2 minus lambda 1. So if you substitute in this equation, you get n2 e raised to lambda 2t equal to n1 0 lambda 1 upon lambda 2 minus lambda 1 e raised to lambda 2 minus lambda 1 t minus 1. So now you can see here the final equation becomes n2. Now if I take this e raised to lambda 2 on the other side, then n2 equal to n1 0 lambda 1 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t. So this is the equation for the number of atoms of B at any time t. So it contains the exponential terms due to the decay of A and B. Now if we want to find out the activity, then activity of daughter product B, activity A2 will be n2 lambda 2 equal to n1 0 lambda 1 lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t. And so you can see here, so this n1 0 and lambda 2 will become A2, n1 0 lambda 1 will become A1 0, and so the final equation will be A2 equal to A1 0 lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1 minus e raised to minus lambda 2 t. So this is a important relationship. I hope you remember the derivation of this, which will be used many times in subsequent lectures also. So the net result of the radioactive decay chain is that if you want to find out the activity of B at any time t, we determine the number of atoms of B, n2 equal to n1 0 and lambda 1 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t, and activity equal to n lambda. So activity of daughter becomes A2 equal to A1 0 lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2. So this is a important relationship, and there are several corollaries of this equation which we will discuss in details subsequently. Now there will be situations where not only the daughter product is radioactive, but the granddaughter is also radioactive. So like granddaughter means when I say C. So when C is also radioactive, one can set up similar equation like we discussed for B, the equation for the activity of C as a function of time. So to set up that equation, you can write this equation dN3 by dt, that is the growth of the C atoms as a function of time, equal to the growth of C is from B, that is N2 lambda 2, and the decay of C is to D N3 lambda 3. Again, you can put the conditions that when the initial conditions when T equal to 0, N1 equal to N1 0, and there is no B and C. So only purely freshly purified parent isotope is there. So under those conditions, how the activity of C will change with time, that is the problem we have to solve here. So already you know the number of atoms of A, how they will change as a function of time, N1 equal to N1 0, e raised to minus lambda 1 T. Similarly for B, we have just now solved the equation N2 equal to N1 0, e raised lambda 2 by lambda 2 minus lambda 1, e raised to minus lambda 1 T minus e raised to minus lambda 2 T. And so if you set up this equation, substitute the value of N1 and N2 in this equation. Rather, N2 you have to put, so that N2 will contain N1 0, and then you solve the differential equation similar way like we solved the one for N2. Then the solution, I am not going into the solution of the differential equation because the same way you can do for this also. So the solution of that equation will be N1 0. Now you can generalize this the lambda factors in terms of K1, K2, K3. So K1 e raised to minus lambda 1 T plus K2 e raised to minus lambda 2 T plus K3 e raised to minus lambda 3 T. So K1, you can see here, the K1 is related to lambda 1 lambda 2 upon lambda 3 minus lambda 1 into lambda 2 minus lambda 1. K2, lambda 1 lambda 2 upon lambda 1 minus lambda 2 into lambda 3 minus, these two are in the denominator. Similarly K3 will be lambda, so the numerator is constant, you can see, same in all the cases, that denominator is varying. So when you have K1 lambda 1 it is minus lambda 1, when you have K2 is minus lambda 2, when you have K3 it is minus lambda 3. So that is how you can see the order in the values of formulae for K1, K2, K3. And then you multiply this number of atoms by lambda 3 to get the activity. So the activity of C as a function of time will be A10, initial activity of parent, into lambda 2 lambda 3. So lambda 3 term has come because you are multiplying N3 by lambda 3, and the lambda 1 term has gone into A10. So A3 equal to lambda 2 lambda 3 upon lambda 3 minus lambda 1 into lambda 2 minus lambda 1 e raised to minus lambda 1 T plus lambda 2 lambda 3 upon lambda 1 minus lambda 2 into lambda 3 minus lambda 2 e raised to minus lambda 2 T plus lambda 2 lambda 3 upon lambda 1 minus lambda 3 into lambda 2 minus lambda 3 e raised to minus lambda 3T. So using this equation you can calculate even the activity of the granddaughter product. And there are several cases you will see that we do produce the radioisotopes by two decay processes. So that will come in the discussion subsequently. Now there can be situations where the granddaughter, instead of being radioactive, is a stable isotope. In fact, this is very common. Just we discussed, when you discuss A going to B going to C, that is the same situation, and the granddaughter is stable. It is not undergoing further radioactive decay. But you can use the formula for the number of atoms of C, which we derived just now, to calculate the number of atoms of C that is formed at the end of the time, some particular time. So what we saw just now, that the number of atoms of C is given by initial atoms of A into this term K1 in terms of K1, K2, K3, where K1, K2, K3 are functions of lambda 1, lambda 2 and lambda 3, and the subsequent the exponential terms for the 3 isotopes. Now it is a hypothetical case now here, because lambda 3, the granddaughter is not radioactive. So in such a situation, lambda 3 becomes 0. If it is not decaying, means the half-life is infinite, so lambda 3 is 0. So K3, the K1, K2, K3, these terms are same as we discussed the previous slide, and I have highlighted this lambda 3 in those terms. This lambda 3 will become 0, and you can see the implication of this in this equation. So when C is stable, lambda 3 is 0, and therefore K3 becomes equal to 1. You can see here, if lambda 3 is put equal to 0, then it becomes lambda 1, lambda 2 upon lambda 1, lambda 2, that is equal to 1. That term is simplified. Similarly, and now the terms, now you can see lambda 3 you put equal to 0, then it becomes n1 0 minus lambda 2 upon lambda 2 minus lambda 1. So this term lambda 1 will get cancelled out, e raised to minus lambda 1 t minus lambda 1 upon lambda 2, 1 minus lambda 2. So the second term, K2 term, so that minus term will come because of the minus lambda 2 here, and lambda 2 will get cancelled with this lambda 2 we have, and then e raised to minus lambda 2t plus 1, the K3 becomes equal to 1. And you can now in fact rearrange this equation in such a way that these terms represent n1 and n2. What is n1? n1 is n1 0 1 minus e raised to minus lambda 1 t, and n1 is n1 0 e raised to minus lambda 1 t. So this is n1, this is n1 0 minus n1, that is at any time t, and minus n2. So minus n2 is n1 upon lambda 1 upon lambda 1 minus lambda 2 e raised to minus lambda 1 t minus is 1 lambda 2 t. So the number of atoms of C at any time will be the initial atoms of A minus the number of atoms of A and B at that particular time, that is n1 and n2. So this is how you can calculate, like for example, if you have a freshly purified parent and after a long time you want to know how many atoms of granddaughter will be formed which is stable, you can use this equation provided you know the number of atoms of n1 and n2 at that point of time. In fact, if you know initial activity, you can calculate n1 and n2 also. So that is how you can try to find out the activity or the number of atoms of the granddaughter. To extend this further into a large series like natural radioactive series, in fact this condition was there in the early 20th century when the scientists were trying to separate the daughter products from the natural radioactive series, and there are a number of decays, like as I mentioned, 238 uranium undergoes 8 alpha and 6 beta decay to 206 lead. So suppose at any point of time you want to find out what will be the activity of thorium 230, which is the 1, 2, 3, 4th product, daughter product, or radium 226, which is the 5th daughter product. So in such situation, whatever we discussed just now may not be useful. So you can go for a generalized equation, and that is called as the Bateman equation. So the generalized equation for a decay chain where there are the parent isotope A decays by subsequent decay to B, C, so on to M, N, and so on, then we can write a generalized equation for nth daughter product like dNn upon dt, where this is the number of atoms and this is the nth isotope. Nm lambda m, that is the growth part, minus nn lambda n, that is the decay part. So this is the similar equation which we just now solved. Now the solution of this equation will be similar to that we found for the granddaughter, but in a generalized way now. And so the number of atoms of n, this particular isotope at any time t will be given by initial number of atoms of A into same terms Ka, Kb, instead of K1, K2 I am putting here Ka, Kb. So Ka, Kb, Km, Kn. So and the corresponding exponential terms e raised to minus lambda A, e raised to minus lambda Bt, and so on. Now here again you can see the order in terms of the lambdas that are being used. Ka will be lambda A upon lambda n minus lambda A, lambda B upon lambda B minus lambda A. So you can see lambda A is in the subtraction mode, minus lambda A in all terms. The Kb is again lambda B minus lambda B everywhere, and Km and Kn. So you can set up the equation, a generalized, in fact you can make a computer program to calculate the number of atoms of any daughter product at any point of time using this generalized Bateman equation. And this becomes very useful when you have to calculate the activity of a daughter product. Like for example, you want to separate 226 radium from a uranium sample, with the old sample, but you want to know a priori what will be the number of atoms or what will be the activity of 226 radium. So there you can do this calculation and arrive at whether it is worth going for separation at this point of time or not. So these Bateman equations are very useful in finding out the activity of daughter products in a natural radioactivity series. Now we will come to another aspect of this radioactive decay chain. Then many a times we will come across situations where, depending upon the half-lives of parent and daughter, you may have the growth and decay of the daughter product in a different fashion. So we will discuss that in subsequently. So again I give this typical case of A going to B going to C, with the number of atoms of A and B being N1 and 2, and their decay constant being lambda 1, lambda 2 respectively. And we derived the expression for the activity of B as a function of time in terms of the initial activity of parent into lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1t minus e raised to minus lambda 2t. So now there are two situations, A, where the parent is short-lived than daughter. So when we say parent is short-lived than daughter, means the T half, the half-life of parent is less than that of daughter. And in terms of the decay constants, lambda 1, the decay constant of parent is more than that of the daughter. So you take note of this one. This is important because there will be many different situations depending upon the magnitude of lambda 1 and lambda 2. And the second situation is when the parent isotope is long-lived than daughter isotope. So that means T1 is more than T2, or conversely lambda 1 is less than lambda 2. So depending upon the magnitude of lambda 1 and lambda 2 or T1 and T2, we will discuss different situations. Now here the first case where the half-life of the parent is short-lived than that of daughter. And I give you a typical example where you have 131 tellurium having the half-life of 30 hours, really a day, 1.25 day or so. It decays to 131 iodine having half-life 8 days, and which is decaying to 131 xenon, which is stable. So assume that we have initially a freshly purified 131 tellurium. So at T equal to 0, the activity of daughter, that is 131 iodine, is 0. In such situations, if you see the activity profile of a daughter product, this is the daughter product activity profile. What will happen is at T, when, so the general equation, what was general equation? A2 equal to A10 e raised to minus A10 lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t. This is the generalized equation for the activity of iodine 131. Now, here tellurium 131 is short-lived than iodine 131. So, the activity of tellurium 131 will decay faster than the growth and decay of tellurium iodine 131. So, what happens? Let us put this condition here. When T is very high compared to half-life of parent isotope, then this e raised to minus lambda 1 T tends to 0. So, that means this term becomes 0. When these terms become 0, then the activity of daughter will change as A10 lambda 2 upon, now that negative sign you can bring here, lambda 1 minus lambda 2 e raised to minus lambda 2. So you can see here that the daughter activity after some time, after in fact a significant number of half-lives of the parent, will decay with its own half-life, where there is a constant term due to the ratio of lambdas. So this I have tried to illustrate in this graph here. This is in the linear scale. So the activity of A1, the parent tellurium 131 will decay exponentially, and from this activity of parent the daughter activity is growing, and then it will reach a maximum, and then it will start decaying with its own half-life. So there is no case of a equilibrium. We will discuss the equilibrium case in the second part of this lecture. So essentially what is happening, that the total activity, if you try to add these two, the total activity will change, and then it is difficult to resolve the parent and daughter activity from this data. This is the total activity. So this is a case of no equilibrium. That means after the decay of the parent isotope, the daughter isotope will decay with its own half-life. There are several cases like these cases, but there are more useful cases when the parent is long-lived than daughter, and then we have a case of an equilibrium. So that I will discuss in the next part of this lecture. Thank you.